Hello everyone, and we're going to continue our journey in biostatistics with chapter 11, Inference About a Mean. In this chapter, we start getting into setting us up to get to different statistical designs, specifically when we start getting to ANOVA and chi-squared and different types of statistical analysis that we can run. But we need to learn a couple more things before we quite get there. In this chapter, we're going to talk about estimated standard error of the mean, a student t's distribution, one sample t-test, confidence intervals for mu, paired samples, conditions for inference. Lastly, we'll talk about sample size and power, but as the class has gone on, I would like everyone to know and read and understand it, but we won't be tested on it or go over it. And there is a problem in the back of the book that talks about power, but I will be helping you through that problem just so you can see. So we're not going to completely dismiss it, but don't stress out about knowing every little detail of it. So let's get started. So we have estimated standard error of the mean. So as you know, in the previous chapters, we used the z-score for hypothesis testing. That is, the z-score formula requires more information that is usually available. Specifically, a z-score requires that we know the value of a population standard deviation or variance, which is needed to compute the standard error. In most situations, the standard deviation for the population is not known. In fact, the whole reason for conducting hypothesis tests is to gain knowledge about an unknown population. This situation appears to create a paradox. You want to use a z-score to find out about an unknown population, but you must know about the population before you can compute a z-score. Fortunately, there's a relatively simple solution to this. When the variance for a population is not known, we can use the corresponding sample value in its place. So, as we were previously using the population standard deviation and our little fancy symbol of sigma here, instead we are now going to calculate the simple standard deviations as S and use this as the estimation of the standard deviation, or sigma. So really, when we take our standard error, which was our standard error over x bar equals, it used to be the standard deviation of the population divided by the square root of n, and you're just replacing that with s, and now we're getting the standard deviation of the sample. So if you remember way back, I believe chapter 4, when we started doing standard deviations, and we had those two different formulas for n minus 1 and then just over n, and I slowly kind of talked about hinting that they're different because there's a difference between the population and the sample and how we're calculating standard deviation, and now you can kind of see where this is all going. So if we don't know the true standard deviation of the population, how do we estimate it? And we use it by calculating the standard deviation with S. So using S instead of the sigma adds a source of uncertainty when we do this, and the Z procedures no longer apply, and we use T procedures instead. So now we're going to be using what's called a student's T distribution. It's a family of distributions identified by Student in 1908, aka William Seeley Gossett. You can read about him. He went under the pseudonym of Student, and this is why it's called the student's T distribution, even though the statistician William here is the one who actually created it. The T family members are identified by their degrees of freedom, which is notated by df. T distributions are similar to Z distributions, but with broader tails. As the degrees of freedom increase, the T-tails get skinnier, and T becomes more like a Z. So to illustrate this example, we have this figure here, where we have df, which is our degrees of freedom, and I didn't mention this, but the degrees of freedom are calculated by taking the number of people in the sample and minus 1, and minus 1 is you'll get your degrees of freedom. If you have an infinite degrees of freedom, you'll see this bell-shaped curve here. It's going to appear very normal, and that is how it's intended. As the degrees of freedom increases, it gets more and more closer to a normal distribution with a bell-shaped curve. But as the degrees of freedom decrease, as you can see, degrees of freedom 9 and degrees of freedom 1, we kind of squish down this top part here. So imagine pushing down and squishing out, and as you do that, these tails, the tail ends come up. And so it leaves more probability underneath these tails with less degrees of freedom, so with less people in your study. So just kind of visually push down from a normal bell-shaped curve, and you can see these tails will rise up as the degrees of freedoms decrease. This is important because this is how t-tests are different from a normal z-test. As we have less people, we might be using a t-test because we actually don't know about the true standard deviation of the population. To go along with this uncertainty and all these cool things that we're learning, we get a whole new table now. So everyone who is tired of table B in the back of the book, or appendix B there, we have a new table now. It's table C, and it's the t-table. And it's found on page 545 in your book. Not only is this table so cool, it's so cool that it's sideways, like wearing your baseball cap sideways cool, and not just a normal straight up and down. So it's a pretty cool table. If you're not laughing, I hope you are. Anyway, so as we look at this table, there's entries in t-values, rows, and degrees of freedoms, and columns and probabilities. So I do want you to take a second, and we're going to take a look at this appendix in the back here in the book. And as you can see, you'll see at the very top of the page that there is a table, and the way it's measured is just like the z-table. It's measured from that point, from your t-statistic that you get, and it's measuring the cumulative probability to the left of the graph. So always remember, we're always still measuring from that point to the left. And as you look down, there's three big bold printed items at the very top, and that's the cumulative probability, the upper tail probability, and the probability in two tails. So a lot of times when we were calculating everything in the previous chapter, we were always using one tail probability, but now we're going to definitely have to get into understanding the difference between one tail and two tail. So hopefully you're very comfortable with one tail, because now we're going to definitely start introducing the two tail within everything. As you look, you have the cumulative probability, which we're all very familiar with from the z-table, the upper tail probability right underneath it, and then the two-tail probability. If you notice, the two-tail probability is always double what the upper tail probability is. So the upper tail will always be to that distribution to the right, and the two-tail probability is going to be both tails and the total number, total probability in both tails. As you work your way down, you'll see the degrees of freedom on the left-hand side, and you'll see they correspond 1, 2, 3, 4, 5 in the first page. And when you flip over, you'll see they go 6 all the way to 30. After 30, they start jumping from 30, 40, 60, 80, 100, 1,000. And then right underneath that, those numbers, you'll see a little z. And that's also to give you a reference back to the z-table and where those corresponding values are in the z-table. And at the very end, you have your confidence level. So let's go back here, understanding the z-table. So just like when we had our z percentiles, you'll probably see stuff where we'll have to find a value with a t-table, and that's noted that let t df comma p, so the degrees of freedom comma the probability, so the t-value with degrees of freedom and the cumulative probability for p. So for example, if we wanted to find t9 comma 0.90, when you go to the back of the book, I know you can see the answer, but let's look this up together. When you go back to the back of the book, we know our degrees of freedom are 9. So that's probably the first place we're going to want to look, 9. And now we're going to find the t-value associated, the cumulative probability associated for 90. So your degrees of freedom 9, find the cumulative probability of 0.90, figure out where your fingers meet, and you'll see you get 1.383 on the table, as noted also here, but this is very easy to read with only a couple of lines. When you actually go to the back of the book and see the big table, it might be a little bit more difficult. So make sure you spend a minute and see exactly how that is found, because we're definitely going to be using that going forward. So that is the t-test and the t-table. And here is an illustrated example of this. As we get to the 10th and 90 percentiles, remember at the 90 percentile we're measuring from this t-test to the left would be 90%. That would mean there'd be 10% above it, right? 0.10. But in the two tails, there's 10% in two tails, right? So if you look at the 9 degrees of freedom at the 90% cumulative probability, but the probability in two tails is 20 because it's added up. 10 and 10 make 20. So this is an illustrated example to show you that. Now we're going to move on to a one sample t-test. So just like we did with our z-scores, our t-test is set up virtually almost the same exact way, except how our standard error is calculated, which, if you remember, we took our standard error and we're not going to be using the sigma anymore. We're going to be using the S for our standard deviation to figure out for an unknown population. So we're going to set up our hypothesis, and now our hypothesis testing is going to be a little bit more formal, where we have our null hypothesis, which is going to state that there's no difference, and we're going to have an alternative hypothesis, which could state either not equal to, which is going to be a two-sided test, or if our alternative hypothesis is going to be less than the null hypothesis, a left-sided tail, or if our alternative hypothesis is going to be greater than the null hypothesis, a right-sided test. Then we're going to calculate our t-statistic using our x-bar minus our null hypothesis divided by our standard error with our sample standard error in there, and with the degrees of freedom, which is calculated by n minus 1. So then we're going to go, and when we get our t-stat test, we're going to be able to convert that to a p-value, and remember, we'll be able to use our p-value to either reject or accept the null hypothesis. It's going to give us our evidence against it or for it. Our significance level is optional. I have included in some stuff, especially in the data set. So if you're still unfamiliar, make sure you see Chapter 9 for guidelines on that. So we're going to run through a sample or a quick question, and then that'll be the end of the first video, and I'll get the next video going. So to run a one sample t-test, we're going to state the problem, and we're going to try to determine, do SID babies have lower than average birth weights? And if you want to see this problem worked out in the book a little bit more, it's found on page 243. We know from prior research that the mean birth weight of non-SIDS babies in this population is 330 grams. When we study 10 SID babies and determine their birth weights and calculate our mean, our x-bar, to be 2,890.5 and our standard deviation of 720. So what we want to know is, do the data provide significant evidence that the SIDS babies have different birth weights than the rest of the population? So we're going to set up our problem. We're going to set up our hypothesis statement, which our null hypothesis is going to state that there is no difference in the population at 330. I don't know why I said 300. It's 3,300 versus our alternative hypothesis, which is our mu, it does not equal for a two-sided statistic, right? Because you don't know what this information is until after you conduct the experiment. So you don't know if they're going to be higher or lower until after you determine the experiment. So when we're setting up, we're going to want to say there's no difference, because we don't know if it's truly going to be higher or lower, because we want to set all this up prior to conducting research. For our test statistics, we set up our numbers in our formula. So we get 2,890.5 minus 3,300 divided by the standard error, which is going to be 720, divided by the square root of 10, and we're going to get a negative 1.8 value. Please note, though, in the back of the chart on the t-table, there were no negative values, so you're always going to take the absolute value of it. When you look, we're going to calculate a p-value of 0.1054, which is going to be weak evidence against the null hypothesis. Now you're saying, like, well, how do you get that? Because when you go into the back of the table here and you look up a p-value of, or if you look up your t-statistic of 1.8, right? Absolute value of 1.8 with degrees of freedom of 9. So you go to your 9, go to your degrees of freedom. 1.8, there is no exactly 1.8, but it falls between 1.383 and 1.833. And truly we don't know where, we know it lies in there, but we don't know how close it is. So this is going to take a little bit of looking at it, and we know the critical value here for the cumulative probability of 0.95 is, we want the t-statistic to be 1.833. Well, it's going to fall short of that, just by a little bit, but it is going to fall short. So it's not going to actually reach the 0.95, and we're not going to be able to truly reject we're not going to be able to reject the null hypothesis at a 0.05 confidence level. And when you actually do the test and look this up, you can actually use calculators, but when we're doing it and we don't have calculators, we're going to have to draw these little conclusions here, and majority of the time I'll have you land on a value and not make too big of an assumption between it. But as you look this up, it falls between it, and if you actually use data software, you'll get your 0.1054 for two tails and a degree with 9 degrees of freedom software. So this will give you the information to actually you can't reject the null hypothesis. And this is just an illustrated example, once again, of the two-tailed p-value SIDS test. So if you go to your p-value of a combined error in both tails, and we get 0.0527 and both tail sides for it to equal our 0.1054. Okay, so take a second, look at this a little bit more. I'm going to end the video there and start the next one up on confidence intervals and do some more examples going through there. But make sure you kind of start looking at the table and knowing how to read it and look at it a little bit more closely. All right, see you in the next video.